Hi, welcome to another lesson at EDU Solutions Institute. Now, today we're actually going to have our final HL topic on the topic of relativity. On last week's lesson, we focused on time dilation and length contraction. So in this week's lesson, let's explore on this principle of space-time diagrams. Now, in this week's lesson, it will be very short because the space-time diagram is just to help us to visualize what's happening in terms of relativity in objects moving in space and time frames. Now, in a space-time diagram, we have two axes. We have the vertical axis and the horizontal axis. The horizontal axis is represented by x, and the vertical axis is represented by the quantity of c times t. Now we know c is the speed of light and t is time. Now in a space-time diagram, the line drawn on a space-time diagrams are called world lines. So if you hear the word world lines, these are just the lines that represent an object's position or motion within space-time space. Now, on a simple diagram for space-time, we have, in this case, two world lines. The central one, which is an angle of 45 degrees, is if an object is moving at the speed of light. Right? So therefore, there is no object that will move faster than the speed of light. Hence, no line would be below that central line there. And then the one above it would be an object that is going slower than the speed of light. So in this case, we have a steeper gradient. All right. Now, if our world line is a vertical line, then that means this object in this reference frame is at rest. So therefore, we notice that the position is not changing, which is x, right? So in space, there is no change in space. So therefore, this object in this reference frame is at rest, right? So what we've known so far is that a diagonal line would represent an object that is moving, right? It's a straight line, so it's moving at a constant speed. Right? We know that a vertical line will give us that the object is at rest. Now, in some minor cases, objects can be accelerated, so the world line would be a curve. Now, if it curves towards the y-axis, then it's a possible reality, because curving towards the y-axis means that your gradient, which would be b over c, would be less than 1. But if you're curving away from the y-axis, then that means your gradient now will be greater than 1. Right? So that means that you will have object going faster than the speed of light, which is not possible. And that's what we see between these two diagrams. Now, we can have a space-time diagram that includes two reference frames. So we have the original reference frame, and then notice here we have the CT prime and X prime reference frame represented by the blue line. So therefore, if you notice, the angle between X and X prime is the same angle between CT and CT prime. So that gives us a second reference frame, right? And then we have a world line of a particle moving along that reference frame. So in that case, if we compare our position between a stationary reference frame and another reference frame, which we can call S prime in this case, we will see that one, the position will change. And that explains to us that we have a length contraction happening, right? So therefore, if we take into consideration how far is it on the x prime plane, and then we compare it with how far it will be on the x frame, then we see that there will be a difference between the starting and the ending point. And that tells us that there is some difference in length that we measure. And that gives evidence that there is length contraction. Right? And this is shown in this position here. All right, so that's the basis in which we look at space-time diagrams, right? So hope you learned a little bit more on space-time diagrams, and I'll see you next week where we continue learning about the IB physics syllabus. Thank you.